Good morning, good afternoon, everyone, and welcome to the last session of the joint conference ICCCBE CIB W78. This session is entitled BIM and IoT Frameworks and Unmanned Aerial Systems Application in Construction. We have 11 presentations, and in between we have a Q&A questions. I'm aware that presenters are impatiently waiting, so I would like to invite the first presenter, who is Caroline Silva Araujo. Caroline, please start your presentation. Yeah, we are waiting just a couple of seconds for Caroline's slides to be up. Hi, Caroline. I would like as well to add, while Caroline is setting her presentation, if you have a questions, please add it to that chat and add the number of presentation, so we know what presentation you are addressing the question to, please. Just a few seconds for the presentation is loading now. Apology for the delay. I can see the presentation is loading. It's taking longer than usual, but please be patient. Some technical issues with Eduardo. He's trying to launch the first presentation. So hopefully soon it will be up. Here we are.
Okay. Hello, everyone. I'm Caroline Araújo, and I will present the paper named Conceptual Framework for Tracking Metallic Formworks in Construction Sites using IoT, RFID, and BIM technologies. Me and the other authors, Leandro Siqueira, Emerson Ferreira, and Diana Costa, are from the Federal University of Bahia in Brazil. The construction site involves a large number of physical resources in its production processes, such as personnel, equipment, and materials. The integrated use of BIM, IoT, and RFID technologies can enable tracking these resources and improve control at construction site. Tracking the ability to determine the current state of an element at any time when you want. Metallic formworks are relevant physical resources in the custom-placed concrete wall constructive system, but after the removal of the formworks, there is a defect corrections that cause rework delay and quality issues. But we can use technologies to control the integrity and service life of the each metallic formworks and reduce this kind of defects. So the main objective is to present a conceptual framework for tracking physical resources in construction site using BIM, IoT, and RFID, in which the metallic formworks are the objects of study. This is based on the research problem. There was the lack of integrated system for this kind of resource, temporary resource in construction phase. So about technologies, Internet of Things allows communication between real and virtual devices and can detect status changes in real time. RFID is part of IoT and can identify and support a large number of unique IDs and the same environment. And the main components of RFID systems are tags, reader, and control software. And about BIM, bioinformation modeling, it has potential to become a digital twin of the reality and supporting the tracking and the monitoring of construction progress in real time. And also have the cloud computing interface and the other technologies. So we did a systematic literature review to identify the main requirements to develop an integrated system with the mentioned technology. So we selected databases, we defined inclusion criteria, and where the search terms should be in the paper. We analyzed all available period in the databases and just papers published in journals. About the review exclusion criteria, we excluded the repeated papers and papers that didn't have BIM, IoT, and RFID as the main subject. So we analyzed it and discussed the results, and in the next slide, I will show you the final sample. Well, there's a RFID BIM with cloud and with the RFID systems with BIM and cloud computing. UADAF systems, RFID systems can provide a satisfactory solutions for most of the applications. Most of the authors reported the use of structured databases in the applications, and some authors use it or recommended the use of a smart gateway in the applications. So the cloud BIM can be deployed through a commercial platform, or we can develop the BIM in Revit, for example, and after this, export and convert it in the cloud. There is a lot of different physical display devices that we can use in the applications and different communication network as Bluetooth, 3G, 4G, Ethernet, Wi-Fi, and ZigBee. There is the first result, conceptual framework with concept addressed and any connections. So we have the construction site, planning and controlling production, specifically in construction phase, and we have the concrete wall system and the metallic formwork with the practical problems. So for tracking the resources, we will need the digital technologies that I mentioned. The operationalization of the concepts is here. So the virtual model we can use to visualize and facilitate communication and collaboration, and digital twinning the reality. And with database, we can interface the other technologies and do the data storage. And with RFID, we are able to identify the elements. There is a full view of the conceptual framework, and you have the products, the integrated system, the products of the operationalization, and we have the user interface to able to manage it and the end user to access all the informations. There is the conceptual integrated system. So we have the real construction site. We need to push the RFID UHF tags in each metallic formworks and use the reader to capture the data and the gateway to communicate with the reader and with the database, and also to generate a local network. So we have the database and we have the virtual construction site corresponding to the real construction site. The end user can use the reader and the integrated system inside a tablet. And the B model will be translated to the cloud to become a digital twin of the reality. There is the three models of the system. The first model is to registration of tags and the respective formwork, and the type of information here is acquisition date, numeric identification codes, and physical aspects of the formworks, such as dimensions and weight. And the second one is maintenance model and can register maintenance history records and service life forecasts, reports, and related photographics reports about this. The last model properly allow, track, and locate the formworks and can provide support during the installation phase to verify and correct assemble problems. But the main objective of this model is to compare the data collected about formworks with the quality of the wall generated using triangulation of all data. There is a full view of the conceptual integrated system, and we are developing this in a real environment now with a construction company partner, and applying this in a real environment, the system based on this framework. The system can collect, store, manage, and display data on an integrated platform. And despite the challenge for the practical implementation, the potential of integrated use of these technologies are remarkable. And the system can improve the information flow on construction sites, the system management decision makes, and promote improvement in management and quality control. Thanks for your attention. Let me know if you have any doubts or questions. And thanks to CNPq for the scholarships and the construction company Gráfico Empreendimentos. Professor, you are muted.
Thank you very much, Caroline, for your interesting presentation. We'll have questions after the first 6 block of presentation. So we'll go first through the 6 presentation. I would like now to invite our second presenter, who is Mehzad Shanimogadam. Welcome, Mehzad. Please start your presentation.
Hello, everyone. My name is Mehzad. Just a second, I have to share my screen. Okay, now you can see my slides, right?
We can't see your slide, Mehzad. We are still...
Hello, my name is Mehzad. I'm a PhD candidate at the École de Technologie Supérieure in Canada. I'm presenting our paper titled as an ontology-based mediation framework for integrating federated sources of BIM and IoT data. And I'm presenting on behalf of my supervisor, Professor Ali Motani. Well, we start with a quick overview of BIM IoT data integration, then we explain the interoperability issues around the scenarios. Afterwards, an overview of our proposed framework will be presented, and finally the expected contributions. Well, the object-oriented nature of BIM enables multiple facets of building to be digitally represented. As a result, there has been an increasing interest to apply BIM for facility management purposes, and IoT, on the other hand.
We can't see your presentation. We can't see your screen. What about if it's not coming up? What about you send it to Eduardo and we can switch on to the next presenter? Is that okay, Eduardo?
It's a good idea, Mohammed.
Yeah. So, Mizad, please send your presentation to Eduardo, and we will move to the next presenter. Is that okay?
Yeah, let's move.
Yeah. Okay, we'll move to the next presenter. Next presenter is Paula Mota. Welcome, Paula. You are presenting again about IoT and mixed reality integration applied on risk maps for construction. Welcome, Paula. Please start your presentation.
Thank you, Professor. Hello, everyone. Hello, everyone. My name is Paula Mota. I am a BIM director at CIPRO Engineer. It is a pleasure to be here and to be able to present this paper that was developed in partnership with Lorena Moreira from Federal University of Bahia and Fernanda Machado from University of Campinas. Risk management in AC industry is a global issue. The failure to handle risk properly may lead to challenges in meeting project proposals. In Brazil, the AEC industry is a high-risk segment due to the dissemination of labor accidents by economic sectors. Risk management is a set of coordinated activities that control an organization concerning risk. Risk include time delays, economic risk, industrial conflicts, and accident at work. One of the Brazilian regulatory norms prescribes that risk map is an essential tool to prevent risk. Digital transformation can improve risk management. This paper reflects that the use of ICT such as BIM, Internet of Things, IoT, and mixed reality, MR, can enhance the traditional risk map process in Brazilian context. Therefore, the aim of this paper is to present a conceptual framework for risk management regarding the construction phase. In addition, we develop a proof of concept. This framework comprises a dynamic risk map using BIM, IoT, and MER technologies. Risk map is a graphical representation of the risk in work environment. It is composed by circles combined with patterns of colors, size, and quantities. Recognizing the limitation of the traditional risk map, there is a demand for the adoption of new technologies. BIM is a technology that increases efficiency concerning security by using dynamic visualization. The potential application of BIM in this context include the association between the BIM object and risk types, the visualization of solution, and the risk control. IoT is defined as a dynamic global network infrastructure that connects objects and real beings with the world and virtual environment. I think stop the slide. So IoT is defined as a dynamic global network infrastructure that connects objects and real beings with the world and virtual environment. Applied to risk management, it enables real-time environmental monitoring solutions for confined spaces zones. MR involves the fusion of the real and virtual worlds. Augmented reality is part of MR that connects virtual objects in an environment. There are applications involving emergency response concerning the AR-based mobile escape guidelines applied to self-evacuation. Risk management is a potential area to integrate MR, BIM models, and IoT. The benefits may embrace the visualization of the risk map superimposed in the real work environment and the control of risk provided by real-time monitoring. These technologies have different approaches. BIM and MER share 3D models and information. MER and IoT integrate by using sensor tracking for visualization, and BIM and IoT integrate through the association of virtual building data and actual data. The frameworks created was the Dynamic Environment Risk Map and the Dynamic Risk Map on paper. The dynamic environment risk map is a condition in which users can access each zones with a display device. In this case, the risk map is visualized with AR technology, and the risk using 3D symbols related to each predicted risk. The BIM model is presented in the natural environment, making it essential to contextualize the risk through the geometric visualization of the construction phase identified. The construction phases can be previously inserted in the system for visualization of AR. The dynamic risk map on paper is a condition in which the 2D risk map is already contained in a place of the construction environment. The users can visualize the risk contextualized in a 4D BIM model, following scales and exhibited in MR. So the application was developed using a BIM model of the Faculty of Architecture at Federal University of Bahia, Brazil. The building has a mixed structure. It's under construction and expected to be completed by the end of 2020. Regarding the proof of concept, the goal was simulating the dynamic risk map with the resource of tracking, sensing, and exhibition. For this prototype, an IoT platform database was used to record environmental data collected by a sensor network. The adequacy of BIM model involved the settings of shared parameters and inserting the symbolic risk object by room. The next goal was synchronize the updated 3D view sets from the BIM author environment to the MER solution. A MER solution is essential to share information, and the synchronizing can be user-based or through automation program to achieve live status. The actual 3D view set with IoT and risk data was synchronized to be accessed by any mobile application. As results, the symbols were visualized at different scales and their IoT data consulted through the properties browser. Regarding the degree of intensity, the higher the symbol, the greater the user risk. Besides, user can access quantitative risk information. So, as conclusion, the framework developed will help the implementation of dynamic risk map. The benefits include the knowledge of risk on site and the reduction of workplace injuries. Future work aimed the implementation for AR sensor solutions and measuring their performance. Thank you for listening. I hope you enjoyed. I want to thank you, Lorena Moreira and Fernanda Machado, for their partnership. Here are our linkages contacts. Thank you. You're on mute, Professor. Professor, you're on mute.
I don't know what's going on with my microphone. Thank you. Thank you very much, Paula, for your presentation. We'll have questions later on. I would like to remind the audience to add questions and add as well the number of the presentation you are asking the question about. And if Mezad is ready, we'll go for his presentation. Otherwise, we'll go with Ramiro. So next presenter is Ramiro. It's a presentation A4. Ramiro, please, you can start your presentation.
Okay, Professor. Thanks. Hello, everyone. I am Ramiro Ballesteros, a civil engineer and master in civil engineering from the Polytechnic School of Pernambuco. And now I am going to present my work title, Unmanned Aerial Vehicles and Digital Image Processing with Deep Learning for the Detection of Pathological Manifestation on Facades. Next, please. In the diagnosis phase of pathological manifestation in facades, the visual inspection stage deserves special attention due to its inherent complexity, height, size, difficulties, and exposure conditions. Next, please. In recent years, the use of deep learning techniques to detect and classify specific features in images and videos has been increasing, which when combined with the use of UAVs for collecting images, is a potential useful tool that can assist the visual inspection. This paper aimed to perform the analysis of digital imaging processing, DIP, for automatic detection of cracked building ceramic tiles associated with a UIV, which will potentially result in benefits like time, cost, and safety with respect to the diagnosis. For the project construction, it was necessary to separate the entire process into modules, starting with the creation of the dataset database. The data is pre-processed with DIP techniques, and finally, the deep learning training and testing stage. With the access of a public dataset to the given problem, it was necessary to create a small database, seeking to meet the minimum requirements of deep learning, even knowing that for good results, thousands of images will be needed for training. In this way, 167 different images were collected, all showing cracks in ceramic tiles. Consecutively, the respective labels were created so that the deep learning interprets the pathological occurrence as a correct answer. In pre-processing step, the images were created so that the result was as close to the labels, that is binarized, with a black background and white strokes. The binarization technique used was the O2 thresholding. Before performing it, it was necessary to apply some other techniques. Next, please. Involving lighting, morphology, and noise filters. This series of techniques made it possible to visualize the cracks in most of the images that previously presented problems. For the deep learning performing, the unit model was adopted. In this way, the architecture was planned to offer good performance even with a small set of images compared to the other deep learning models. Next, please. This step was performed under the Arch Linux operating system, performed with 10,100 images. The step took about 10 hours to obtain more accurate results in the 67 test images. In a way, the model results tends to improve as the data volume is increased, making it possible to spend more time in the training stage and suffer less overfitting problems. The results of the study provided, even under the limitation, a good analysis of the scenario and good segmentation in the images, both images with a lot of noise, as well with discrete features. The inspection showed deep learning proved to be adaptable to complex situations and flexible to obstacles. However, the lack of a public data set available for these types of problems directly influenced the performance of deep learning, limiting the results. It is important to emphasize the importance of a wide dataset to work with deep learning, with good quality and labeled images, in order to obtain better results. Even after selecting the most relevant data to compute the dataset, even so, in many cases there was great variation in the images, such as angulation, distance, and quality. In addition, the preprocessing of the data also impacted some of the results, as it didn't meet all the images in the dataset, mainly due to the variation in lighting. Next, please. The detection of cracks by DIP techniques is feasible from a technical point of view. However, it is considered a complex job when there is high variation in the study images and in a limiting scenario, such as the lack of public dataset for the problem. The project still managed to develop a simple and efficient methodology to what was proposed. There is a promising way to improve the project, seeking to further simplify the approach, minimizing the pre-processing step, for example, and improve the accuracy of the results. In conclusion, there is sufficient evidence to emphasize the potential of digital imaging processing for facades inspection. This method, combined with photographs collected by UAVs, especially through collection techniques that standardize the photographic records, will provide a service with greater security, greater speed, and lower cost, requiring fewer resources compared to traditional inspection methods, such as industrial mountaineering. In short, that is all I had to present. Thank you very much for your attention.
Thank you very much, Ramiro. Very interesting presentation. Thank you very much. We'll move now to the next presenter. We'll have questions later on. Move to the next presenter, who is, are we taking the Mezad or Bruno, Eduardo?
Bruno.
Bruno, okay. Okay, next presenter is Bruno Silveira. Welcome, Bruno.
Hi, Professor.
Welcome. You can start your presentation now.
Thank you. Hi, everyone. My name is Bruno, and I'm going to present the paper Using UAS, Unmanned Aerial Vehicle, for Roof Structure Inspections at Post-Occupational Residential Buildings, also written by Roseneia Mello e Diana Costa from Federal University of Bahia, Brazil. So, roof inspection is essential to maintenance process of a building and can lead to fewer pathologies occurrences through the identification of problems of usage, incorrect design, and poor execution. But there is two main shortcomings faced by this process. First, the inefficiency of manual inspection, and second, the time consuming. Therefore, the research problem is the need to test new technologies that can contribute to the solution of these presented problems, and the main objective is to evaluate the use of UAS for roof inspections on post-occupational buildings, proposing a protocol for flight planning and data collection. The method was divided in theoretical background, then identification of items on the roof that can be inspected through images collected with the UAS, creating a checklist, succeeded by a case study, starting with a UAS mission planning to map the sequence of buildings to be followed, as shown on the image on the left, and how we will take the photos from each tower right below. For data collection, the DJI Phantom 4 and the checklist developed with 28 items were used as tools, applied in a total of 10 projects, with 167 roofs inspected, and the average flight time was 26 minutes per project. After the data collection, the images were analyzed, identifying the degree of conformity of the checklist items and the number of pathologies according to project delivery age. Critical pathologies were highlighted and all analysis shared with the stakeholders. The next step was the training of the maintenance team of the company to use the UAS, and finally, the statistical data analysis and the assessment of results. The 28 checklist items were analyzed by two aspects, visualization and nature. Visualization was divided in items visualized, non-visualized due to technology limitations, and image without sufficient detail. And nature divided in maintenance use related items and items related to construction problems. Also, the interviews and interviews in the questionnaire were applied to the maintenance team to gather the perception. The items visualization analysis on the pizza graph shows that 21% of the checklist items could not be observed due to technology limitations, mostly related to items inside the buildings. 7% could not be visualized due to items of difficult identification, as those related to roof tiles conditions, and last, 20 of the 28 proposed items of the checklist could be visualized with ease, evidencing the potential of applying these technologies for this purpose. Next slide, please. So the present analysis shows the rate of pathologies per roof on the vertical axis throughout the year's horizontal axis. As expected, the tendency is to increase the rate of pathologies the older the building. So the two selected rates in the graph correspond to buildings out of the pattern, that is, Project J and H, possess more than 5 floors per tower. That fact could be what led to a higher rate of pathologies on these buildings, since a higher number of residents can implicate in more services involving access to the roof. Next slide, please. This graphic ranks the most recurring pathologies identified during all roof inspections, and the top 4 were presence of residues on the roof, presence of rusted metals, failures on the waterproofing of the parapet wall, and good integrity and cleanliness. Only then together form more than a half of the 202 pathologies observed. Also, the pathologies were classified according to its origin, maintenance in orange and execution in green. As an example, the top 1, residues on the roof, is of maintenance. Next slide, please. Here we have some examples of the pathologies observed by analyzing the images collected with the UAS. On the top we have the corrosion of metal parts, damaged tiles on the left, and uncovered opening on the right. Next slide, please. As mentioned on the method presentation, the researchers conducted 4 hours of theoretical lessons with the maintenance team, as shown on the left, and 4 hours of practical lessons in open field with the UAS on the right. The questionnaire applied to the maintenance team was ranked according to a relative importance index that you can check with more details on the full paper. The questions applied refers to training in the inspection process with the UAS. The highest ranked items were the quality of theoretical lessons, reduction of physical effort to perform the inspection, they both with maximum rate, and reduction of time spent to perform the inspection in the field with 0.98. Next slide, please. As benefits regarding the use of UAS for roof inspections can be cited greater agility in the inspection process, increase inspector safety, allow easy and fast access to roofs, improvement on the report analysis, and good acceptance by residents. As barriers, the resident curiosity can cause distractions to the pilot. The impossibility to perform flight in roofs near to the airport, possibility of accidents due to inadequate flight planning, and the time spent during the manual elaboration of the report. As conclusions, the findings point out the potential of the application, provide a great amount of data in a short time, allowing the visualization of pathologies in difficult areas. And as further research, it is suggested the report automatization by linking real-time the collected image with non-conform items of the checklist. Thank you for your time and attention.
Thank you very much, Bruno. For the audience, if you have questions about this presentation, this was presentation 5. We'll move now to the next presentation. Next presentation is by Paul Debut, Multi-Scale Flight Path Planning for UAS Building Inspection.
Yeah, hello everyone, and thanks for joining me for this presentation. Yeah, we can start. the application of UAS in the inspection of bridges and other infrastructure has grown over the last years due to the possibilities it offers to reach parts of the infrastructure that are far away and not accessible for humans. And we apply it on different bridges in different areas to detect cracks, damages, and deformations. And for this, we need to pre-plan our flight missions. Here you can see two examples of routes we planned, one for a bridge deck and one for a section of a bridge, including the piers, because the human pilots are often not able to correctly steer the UAV in the height that it's required. In this paper, we propose to use a multi-scale building inspection where we define different levels of interest for different parts of the structure, between low, medium, and high for different purposes, between just getting the rough geometry and then precise crack detection in the highest resolution that's achievable. And for this, we plan different flight plans on rough models that exists. That can either be simulation models from FEM or models from previous inspections. Those models serve as the basis for the plans that orient on the geometry of the bridge that we're inspecting. I'm not seeing the indicator. Yeah. The general approach for us is that we select a large set of possible viewpoints from which we select only the viewpoints that we really need. And to bridge this, we compute a visibility matrix that contains which viewpoint can see which part of the structure, and then select from this, based on this matrix, the points. For each triangle of the mesh that we use, we compute a viewpoint candidate that's placed directly over that triangle in the distance we computed between 20 and 1 meters, corresponding to the interest level. Yeah. And then for each viewpoint, we can compute the part that is visible. In this example, you see only a small part of the pier is visible from that viewpoint, while the rest of the bridge cannot be viewed from this. So we have to choose from all those available viewpoints those that are required, because each viewpoint contains more than one triangle, so not all of them are required. And then we can compute this visibility matrix. You can see a small part of it here that contains one row per object point and one column per viewpoint candidate, and the value in that matrix is set to either 1 if that object point is visible or 0 if not, and we get a really sparse but really big matrix of millions of points and thousands of viewpoint candidates. Then we have the set multicover problem, which is select the minimum number of viewpoints such that all object points are contained in at least n sets. And for structure from motion, the 3D reconstruction, we chose n to be 3, so we have some robustness against errors and possibly bad images in the coverage. And then we start by fixing the columns that are required for the coverage, check if all viewpoints, if all object points are sufficiently covered, and while they are not, we select columns according to their value until all object points are sufficiently covered, and then export the final flight path to the UAV. Fixing the required columns means that if an object point is only visible in 3 images, as here is seen with P2, then we have to select all those viewpoints that contain that point. We reduce the complexity and size of the optimization problem in this case, which really helps and speeds up because it's an NP-hard problem that it can take a lot of time to approximate. And then we compute the value for each viewpoint, which is the number of object points that are not yet covered that would be covered by that viewpoint. For example, here viewpoint 3 has a value of 4. It's higher than viewpoint 4 and is therefore selected. So in the next step, we have an updated value matrix that shows that we still need viewpoint 4. We applied this method to a bridge near our university, the Chacondatal Bridge, which is relatively new, and it's integral with stiff connections between the piers and the bridge deck. It's relatively new, but due to this stiff connection, there are already visible damages and cracks in the piers that we were inspecting. So here on the left, you see a picture that we took in a previous inspection, and we applied a machine learning-based crack detection method to these images. And on the right, you can see a detail of that image and 2 detections where we suspect there could be a crack. And this suspicion we want to prove if it's relevant for the stability of the bridge. Therefore, we put an interest level on each part of the bridge, where we say, okay, the part that is contained in the image is the highest interest level, the rest of the pier is the medium interest level, and the entire section of the bridge is only in low interest level because we're not suspecting cracks there, but we need it for the complete context of our reconstruction and for completeness. And from this, we can compute a flight path, shown here on the right, where we have in total 65 viewpoints, and we have the important region in a high resolution where we have around 5 viewpoints per square meter, whereas for the low part we only have 0.04 viewpoints per meter. If we had inspected the entire bridge with the high resolution, we would have had about 15,000 images. One of these images can be seen here. It's like from 1 meter distance of that pier, and it shows in clear resolution if there are cracks or not. And in the next slide, these are 2 details of these. The left is indeed a crack, and the right is a false positive detection. Those are the corresponding details of the that I showed previously in a much higher resolution. Especially on the left side, you can clearly see a crack in fine detail. But we found out it's less than 0.1 millimeters wide, so the relevance for the structure is not given. So in conclusion, that these multi-scale flight plans can help acquiring these informations that we need to maintain our bridges. They can support experts in the inspection and can be the base for a digital maintenance strategy for our infrastructure in extending the service life. For the future, we want to work on this further. We want to include constraints that improve the reconstruction that's possible from the images. We want to include the flight properties, and of course there's always a chance to improve the algorithms we use a better solver for the optimization problem with better results and better performance. Thank you for your time.
Thank you very much, Paul. Very good presentation. We will check if Mizad is here. If it's not ready, we'll go to the Q&A. Eduardo, should we go for the Q&A, or do we have Mizad presentation?
Q&A, Mohammed.
Okay, great. That's great. Okay, guys, let's start with the Q&A session. I'm going through the chat to see where are the questions. There are many questions here for the presenter, so let me have a look. I have a question here for presentation 5, which is Bruno. Can you read the question, Bruno, here, or you want me to read it?
I can read it.
Yeah.
Thank you, AKP, for the question. He says, nice concept, Bruno. Looks like a solid research. Could you elaborate more on the technique of inspecting the photographs? Is there a potential to use the AI to recognize issues in the future? So the images on the studio in these inspections were analyzed without any computer aid, but I think it's very possible to apply machine learning to identify pathologies, patterns, or even image pattern recognition. The main barrier that we're trying to improve is on the time spent for generating the report that comes out as a result of the inspection. But the images are still being analyzed manually. But there is room for it, for improvement on this part.
That's great. Thank you. There's a question here for Paul. Okay, can you see it, Paul, here?
Yes. The question is whether we plan to apply this method to other structures than bridges. And yes, we do plan to. A part of our research project is also to apply this method to, for example, retaining walls that are adjacent to roads, for example, or to dams that hold the water reservoirs, or, for example, even to tunnels. While tunnels are a little difficult using drones, but the approach of using image analysis methods for building inspection can well be applied to tunnels, and the arrangement of images or the arrangement of viewpoints for the inspection of tunnels is also part of our research.
Great, thank you. I don't see other questions here. I can really quickly, if possible, give every presenter the chance of dealing with some questions. I have really quick questions. So the first question really is to Caroline. You mentioned this framework for integrating the three IoT, BIM. Sorry, I have. So you mentioned, Caroline, the framework for integrating BIM, IoT, and RFID. You mentioned some application which is formwork. Do you have other use cases where we benefit from such an integration?
We are starting the implementation now in a real case with a construction company partner, and we are in the phase of defining the tools, because there is a lot of different tools that we can use for compose the digital twin and the database. So you are using the Forge Autodesk now for compose the digital twin, and Firebase as a non-structured database. We are trying this, and we will do more tests in construction site in the next days. The next step. Thank you for the question.
Thank you. I will have to go back to the question of the audience instead of asking mine. I have a question again for Caroline. Do you consider the use of BLE tracking for your system?
Yes, you consider this, but now we are focusing on RFID applications. In the future, we will have the intention of to use drones and BLL also in the extrudery. But now we are focusing on just on RFID.
Thank you. Paul, there's a question for you on the screen here.
If we consider taking overlapping pictures, I suppose that didn't really come through in my talk. That's the really important basis of the work, that the images are overlapping and are overlapping by quite a lot. So we're aiming for around 70 to 80% overlap for the images as we're using them for the photochromatic reconstruction. I was trying to say this, that we need each point to be in 3 images, which in turn means that the images have to overlap to contain those points. I realized while speaking that I had a lot to talk about.
Thanks, Paul. I have a quick question for Paula. You mentioned risk maps, and obviously in doing risk management or risk assessment is really important to be accurate, especially on construction site. What data your technological solution needs in order to estimate the risk? Where do you get that data from?
All right, thank you for the question. Actually depends on the risk. If we have to make sure that the worker is safety on the environment, right? So the data depends of the type of risks they are present on the environment, and the potential risk on the potential various number of the risk, like it's too hot, it's too cold, it's too high, so it depends. And this we can grab this, we can take this data from external database and input this in the BIM model.
Thanks, Paula. There is here really a last question. I know we need to move to the next set of presentation. Again, it's for Paul. Can you say, Paul, how accurate is the localization of UAM?
The accuracy is GPS based. We have a high precision GPS system on the drone, but it's still GPS based. So especially close to the bridge, we're getting into trouble with high precisions. When we're flying less than a meter from a bridge away, GPS will not work for us. So at the moment, we have to use a mixture between manual flight in those critical areas and GPS-based flight for the parts where we have to rely on the camera to reach the precise position. We are working on including more sensors to the drone that can then, for example, work with a defined distance, where we say, okay, please keep 1 meter distance between you and the surface and follow the surface. So then we can guarantee a safe flight while also reaching the precision and accuracy goals that we have.
Thank you very much. I think with this we concluded the Q&A for the first set of questions, for the first set of presentations. We will now move on to the next set of presentation. Thank you very much for presenters in the first part. So we'll move on now to the next set, and the first presenter is Leon Price. Leon will talk about dynamic crane workspace update for collision avoidance during blind lift operations.
Mohammed, they are not in the room yet.
Okay.
Please, next presenters enter the virtual room so that we can.
Okay.
Patricia is here.
Yeah, should we move to Patricia?
Okay. Second, Patricia.
Hi, Patricia, and welcome. So, Patricia, if you are hearing me, if you should you can start your presentation.
Hello.
Hi. Yeah, you may start, Patricia.
Okay. Good day. My name is Patricia Peralta. I'm a PhD student, and I will be presenting the paper Beam-Based Concrete Printing. Additive manufacturing, or AM, of concrete structures refers to sorry, there was some overlapping. Refers to computer control processes that extrude and precisely place concrete in a layer-by-layer basis to manufacture concrete components. There is a lack of knowledge on inter-process relationships in concrete printing. Therefore, expertise and real-time monitoring is required. Also, conventional AM data modeling approaches are implemented for concrete printing. Conventional AM data modeling is based on traditional solutions such as standard tessellation language together with G-code. And there are information breaks along the digital thread, and unique conditions specific for concrete printing are not taken into account. New data modeling models are required to allow standardization of the data triplets, such as process information, material information, and geometry information. Therefore, we develop a semantic modeling approach called printing information modeling, or PIM. The approach is a semantic representation of specifications for concrete printing jobs in the shape of a meta model. It may be implemented into the IVC standard, unifying the data triplet into a printing information model. In literature, parameters and interprocess relationships have been documented and may be characterized according to the data triplet. For process parameters, we have hardware-related parameters in components such as pump system and printhead, and manufacturing-related parameters in components such as filament and toolpath. For the material parameters, we have that the sealing reactions of concrete show strong interactions with process parameters and with the specific printing strategy. The concrete parameters include mix design, material specifications, and material properties. Regarding the reinforcement, it is dependent on the concrete printing method used. The geometry parameters may be inherited from the BIM models, such as dimensions, point definitions, and geometric objects and their representations. Also, there are geometric parameters related to additive manufacturing process, such as the contour lines, the results from the slicing processes. A meta model is then developed, the printing information model or the PIM model. The parameters are grouped into classes, and the interprocess relationships are represented with associations, dependencies, and generalizations. The meta model is comprised by process information, material information, and geometry information. For example, if we focus on the toolpath data, we can observe that it's a subclass of process information. It uses contour lines to define a path. Likewise, while defining the path, it also uses fresh state properties of the concrete data and filament data to ensure the geometric precision and the buildability of the concrete structure. Later, the motion data follows the path stored in the toolpath data. In this way, concrete printing job specifications may be semantically represented and then may be used for developing new or expanding existing standards or software applications. Using the PIM model as basis, we develop a BIM approach towards concrete printing, incorporating the data triplet into a single data model. We developed the PIM test application, which implements the PIM model using IFC models as inputs and generates CNC code as output. First, using IFC models as inputs, the 3D geometry and the material specifications are extracted. The PIM test application then incorporates the process parameters and the material properties specific for a concrete printer and a concrete mix. And finally, CNC code is generated as output and transferred to the printer. The BIM approach is validated with an L-shaped concrete wall that is designed in a BIM tool and exported as an IFC file. A concrete with 30 megapascals design strength is specified as the material, and it has an 80 millimeter height and 150 millimeter thickness. The validation test is carried out using a gantry printer. The printer uses a custom concrete mix of 30 megapascals. And for the printing test, a printing speed of 100 millimeters per second, a pump pressure of 1 megapascal, and a layer height of 40 millimeters is defined. And a unidirectional printing strategy is implemented. As a result, a CNC code is obtained, as well as a visualization of the toolpath, as shown in the figure. The toolpath visualization allows to evaluate the geometric precision and the CNC code generated by the PIM test application. The CNC code then is read by the concrete printer for a printing test. As a conclusion, we have shown that the PIM model semantically describes the AM digital triplet, facilitating instantiable models for BIM-based concrete printing. The PIM model is the first step towards standardizing the digital data triplet. Also, the application uses BIM models as input source to generate CNC codes. As future work, further studies may be focused on optimizing an AM algorithms for calculating toothpaste and on incorporating sensor data for processing, monitoring, and real-time printing adjustments. Additionally, in the future, the IFC schema may be extended to support process parameters and for the material parameters. Here are the references used for the PIM model. Parameters and inter-process relationships are described in more detail in these studies. If anyone is interested, you can take a look. And thank you for your attention. If you have any questions, don't hesitate to ask them.
Thank you very much, Patricia, for this excellent work. We'll move on to the next presenter. I am going, Eduardo, to the next presenter, Ben Jowett, if that's okay.
No, the next. Okay, let's go to Martina.
Okay, yeah.
Return to Martina, okay?
Okay, that's fine, yeah. So the next presenter is Martina Filardo. So Martina,
hi.
Welcome to the conference, and you may start your presentation, please.
Thank you. Good evening. In the next 6 minutes, I will be talking about our paper on installing reinforcement rebars using virtual reality and 4D visualization. My name is Martina Valentin Filardo. I am a research assistant at the Bauhaus University in Weimar, Germany, with a background in architecture and construction management. I will start by talking about our setting and aim, explain the created workflow shortly, as well as the steps we took in modeling, 4G scheduling, animation, as well as the VR implementation, and finish with a short conclusion and outlook. So our initial situation was we had a 2D set of drawings Oculus Rift equipment, corresponding hardware, and access to diverse software licenses. Our aim was to generate a visualization in VR for a head-mounted display equipment from a standard 2D drawing set. The created workflow started with modeling the pillar based on the mentioned drawing set. The 3D BIM model included parametric editing and distribution. To create a 4D model, we took the sequencing reference from a Gantt diagram based on standard scheduling tables used widely in Germany. This was used to create an animation based on the modeled rebars, which were divided into sets and included their direction. Subsequently, we created a project in a game engine with the objects and imported the mentioned animations. We used Lua scripts to communicate with the HMD and flow nodes for the user interaction. Mainly, we used Autodesk Revit for modeling, 3ds Max for animation, and 3ds Max Interactive for the game engine, and the mentioned Lua scripts and flow nodes for the VR implementation. Of course, we also used the Oculus application. The used software was mostly Autodesk-based, so compatibility was not an issue. Next, you'll see excerpts of the reinforcement modeling divided into vertical and horizontal rebars, which were modeled with either the freeform or the sketch tool according to their reference plane. Certain sets were also divided into subsets, as you can see on the right side, where 4 rebar form 2 cages. While modeling, we also set the material properties. Also, the number of rebars in each set varies according to the type of rebar and their position. These rebar sets play a very important role in the next steps, since the sequencing and animation clips are based on them. An often mentioned pro of using the BIM method is the additional visual examination of the model. This visual examination was also needed in this project in order to correctly model it. We ended up noticing missing information in the 2D drawing set, which would otherwise just be noticed on the construction side. Our next step regards the rebar scheduling. For this, we created the mentioned Gantt diagram for each rebar set, based on scheduling tables used widely in Germany since the 80s, thus creating a 4D model. The sequence starts at the bottom and moves up, and after assigning the sequence to each rebar set, the color-coded model on the right side was created. The sequence of rebar sets is the basis for creating the animations, which result in the visualization of the installation process. To create these animations, we still need one information, the direction from which the rebar sets and subsets move into their final position. For this, we animated the movement backwards, starting at the final position, and then inverted them to the final position again, so it becomes the final position also in the animation. This way, we always just needed to change the value of one axis, either in the positive or in the negative directions. After assigning the directions to each rebar manually, we divided the animation sequences into equal frames and divided them into clips for each rebar set. This is important for the play and pause options later on. All the rebar sets move directly into their final positions from either the X, Y, or Z directions, either from the positive or negative values. Side note, since this is a 2.5D object, sets cannot move from the negative Z direction since there is the terrain. Next step is the implementation in the game engine. For this, we used, as previously mentioned, the 3ds Max Interactive application, which uses the Autodesk Stingray engine at its core. We started with a basic project and imported the rebar layout model, as well as the animation clips, placing them in one scene on a single level. 3ds Max Interactive has an integrated Lua app kit. Lua is a Brazilian programming language that allows communication between game engine and the head-mounted display equipment. We use default scripts from the app kit, which are the scripts on the top, as well as custom scripts, which are mainly the ones at the bottom of the diagram. With this, we were able to visualize the movement of the rebar sets in the defined sequence within the VR environment through the Oculus Rift equipment. Examples of rebars moving in from each direction, that is, positive and negative X and Y and positive Z, into their final positions can be seen on this slide. However, a key component of the virtual reality is the user interaction. In addition to moving around the model in the scene, we also implemented user interaction through flow nodes with actions like play and pause, triggered by the buttons on the virtual hand controllers connected to the animation clips and enabled by the Project Lua script. As can be seen on this slide, the user can see the rebar sets moving in through the head-mounted display equipment. He or she can play and pause the animation and move around or near for a better view. He or she can also see the kind and diameter of the rebar in question. And with this, we arrive at our conclusion. We are able to achieve a VR-based visualization of reinforcement installations through many steps and different software applications, which was expected given that there are not many interfaces or overlaps between BIM and VR software, so that changes in the reinforcement layout require redoing almost all steps. We also found that modeling and programming skills are of vital importance for this task, which needs to be considered when educating professionals. The used hardware is compatible with German construction sites to a certain degree. If used commercially, the licenses of the many used software applications can become pricey. That was it. I hope you could understand what we did, and thank you for your attention. Obrigado.
Thank you very much, Martina. We definitely understood. Thank you very much. A very good presentation. Eduardo, should we move to Ben? Hi, Ben. Welcome to the conference. You may start your presentation. Thank you.
So will the presentation automatically? Oh, there we go.
Yeah.
Great stuff. Okay, so this is the presentation regarding the paper of Field BIM, establishing a requirements framework for mobile BIM technologies, co-authored by myself and Mohamed Kassem out of Northumbria University. Next slide, please. So a little bit about myself. I've been in construction now for 11 years, a background in construction management and transitioned into BIM. I'm currently studying a PhD researching mobile BIM technologies, and I've been using field solutions for around 6 years now. So this particular paper is part of a wider piece of research where we're looking into mobile BIM technologies and field BIM, promptly looking at a requirements taxonomy, benefits evaluation approach, and also looking at supply chain performance and how all that can be derived from mobile field BIM platform. So the paper presents the findings or initial findings of part of this work. So the current situation, there's a consistent diagnosis of inefficient practice and low productivity, and BIM is always put forward as a proposition to improve efficiency and productivity in the industry. Next slide, please. There's obviously a lot of research into various different model uses, but a lot of those model uses tend to focus on the pre-construction period rather than during construction or operation. And equally, the percentage of the workforce that work on site accounts for a much larger portion than office-based roles. So that leads us on to mobile BIM technologies and field BIM still not being widely discussed, and a lot of interchangeable terms are used, such as field BIM, site BIM, cloud BIM, mobile BIM. So a key piece of this work is to distinguish what those terms mean and to distinguish between mobile BIM technology and field BIM. So there are some early studies that have investigated the benefits of field BIM, some reference there. But there's also an emphasis on the importance of cloud technology and the security that underpins that. However, some studies have shown that the percentage of apps that facilitate model access is low. So the methodology is a grounded theory approach. So it's an inductive study where we're looking to build theoretical constructs, use adequate sampling techniques of participants and case study projects. And this is through a longitudinal case study. So several research methods have been used, a case study project, which consisted of a launch workshop with the project managers, a survey at the end of the project after 1 year, and also an independent expert review of the platforms that had been used that was external to the case study project. We also undertook a focus group with experts to identify business level requirements, not just project level. And we've also done a survey of the industry to understand how it's been used. However, this paper only reports on the first two methods, so we'll look to expand that in future work. So the case study project was using federated 3D geometrical models during design and construction. It was using a field BIM solution with associated workflows. It was adhering to level 2 BIM under the PASLM 92 Part 2, the older standards, and it was also adopting non-proprietary data formats. So the launch workshop was undertaken with the 10 number site managers on site. They had no prior experience of mobile BIM technologies, and the launch workshop was undertaken during REBA stage 4, so the technical design stage, which sort of overlaps with construction. The outcomes of that workshop to understand the team's requirements included the ability to produce digital forms and tasks, the ability to view 2D and 3D on site and compare with the real world, view various document types such as PDF, and also supported by iOS and Android. We also undertook a survey 1 year later with the same site managers in a questionnaire format that was a combination of Likert scale questions and also free text responses to really get under the hood of things that might not have been considered under the Likert scale questions. And here's some of the outputs from that survey, and you can see a generally positive response around the viewing of 2D drawings and 3D models on site, the ease of finding things in a model remotely, and the downloading of documents. There's also an outlier at how good the app was at viewing issues and forms, which can be described down to training. The independent expert review also consisted of open-ended probing questions that covered the functionalities of MBT to really just get under the hood of what an independent expert thought of this platform. So it covered the viewing of models, the creation of tasks and forms. The outcome of that essentially defined that the MBT was able to support the golden thread of information by building up a legacy of data throughout the construction and handover process, but also noted the need for thorough training of the site team and subcontractors to make it successful. So the results of that all together combined noted that there's gaps in literature and there needs to be some clarification around the terms that are used when it comes to field BIM. The development of a framework that links use cases with benefit evaluation and MBT requirements as well. Future considerations, data security, the data excess impact, so what is the result of too much data, and then also the potential skill gap and the ease of use of these platforms for site teams who are not used to using 3D content and data on a day-to-day basis, unlike office-based roles. So the future work will be to confirm the findings through further qualitative and quantitative data, such as surveys and more MBT data from more case study projects, and also extend those requirements to a project and an organisational level to understand both tiers of requirements when it comes to field BIM, and both of those combined should lead to an MBT requirements taxonomy.
Thank you very much. Thank
that
you.
went very quick.
Yes, indeed. Thank you very much. So we'll have questions later on. This was presentation 10, if you have questions about it. Now we'll move to the next presenter, who is James Wakefield. James Wakefield will present improving site access verification and operator safety in smart cities, a pilot case study. Welcome, James, and you may start your presentation. James, your mic is on mute.
My apologies. My apologies.
Thanks.
Thank you. Hi, everybody. I'm here to present my paper, which is part of a wider PhD research. I'm studying with Northumbria University under Mohammed Qasim, the chair of this session, and I'm presenting on improving site access verification and operator safety in smart and sustainable cities. And what I plan to do is take you through a pilot study in a UK decarbonisation project. Thank you. So the basic premise for the research is that the built environment is changing very, very rapidly, and we are living in fact, over the next decade or so, it's predicted that $78 trillion worth of investment will be required for global infrastructure. So we're working in an environment that's changing very rapidly. These new environments, smart environments or smart cities, are digitized. And when they are digitized, they are smart built environments are sustainable. So if we've got a smart environment, the idea is that we can make it sustainable. The catch is that smart cities are much more complex than the regular built environments. We see lots more assets, we see sensor technologies, we see gear to process all the data that's being collected, making those environments much more complex. And with increased complexity in the built environments comes a broader risk profile. So where we find more complexity, we find more and most importantly, new risk, which we have to mitigate against. We can see that the digitization of the built environment has the potential to inform safety. And in fact, the PAS 1192-6 standard, which is the current standard, in fact, currently being updated, shows how we can recognize health and safety issues in environments such as BIM, or processes such as BIM, I should say. My specific area of focus is on individualized training experiences that are powered by those digitized built environments, meaning that people who come to service them can have more engaging, more relevant, more appropriate, and more timely training. The use case that we looked at was the High Deploy project, which is currently running at Keele University. The bottom line is, we inject 20% hydrogen into the gas network, we drive down carbon emissions by 20%, and it's here at Keele University where this concept's been proven. As I mentioned previously, though, when you implement new technology, this is a test, by the way, scheduled to be rolled out across the UK over the next decade. This test is currently running for approximately 12,000 people using the campus daily. And with that new technology comes new risk. That means that the operatives that are responsible via the network provider, a company called Cadent, the operatives that are responsible for maintaining the environment, the regular environment, are, when they come to Keele University, dealing with new risk. And that means that at Keele University, we have to control the contractor access to the site in some other way. We have to add new elements of control which ensure that those coming onto this site to service this site understand what the new risk is in this decarbonisation project. In order to develop this research, we had a three-stage qualitative content analysis. And basically what we were looking to do was look at the situation pre-high deploy. What were the arrangements for coming on site access verification arrangements pre-high deploy? What are those arrangements now that we have high deploy in place? And what might those arrangements look like with our proposed solution for improved site access verification? We essentially, as the statement says there, we were looking at the key stakeholders to find out and work with them to find out their level of confidence in the contractors coming to site. Basically, the process now is that, or pre-high deploy, there was general, largely static site access verification control. You had a small handful of credentials that needed to be met. If you met those, you could come on site. Once high deploy was rolled out, and as I said, when high deploy is rolled out, we get new risk. Kiel University, as the estate operator, had to go ahead and implement some new form of training into their site access verification to make sure that those coming on site are able to be compliant to come onto site. What we said is that we would like to introduce a dynamic process to ensure that the most relevant information was available to the contractors coming on site at the point when they most needed it, i.e. just before coming onto site. What we found was that the current process does ensure that operatives are access verified. However, the feedback from the two key stakeholders, this is one expert from the Kiel estate and one expert from Cadent, the network provider, suggested that their confidence in the compliance of their operatives and the ability of their operatives to be safe when they were working with this high deploy network where 20% hydrogen was present, their confidence in that position was increased. What they identified as potential downsides were that the way that we were proposing to communicate these micro credentials ahead of those contractors coming on site meant that a lack of face-to-face training could alienate some stakeholders, and also that e-learning can be frustrating. I think everybody that's online now will attest to that. E-learning can be frustrating at times. The current arrangements, the conclusion is that the current arrangements present change management challenges. Proposed solution supports those change management challenges so that increasingly dynamic risk profile that is encountered in the smart city is able to be mitigated and managed in a more effective way where this solution is present. I think we might have frozen on that last slide. Next slide, please. And also, I just wanted to mention that the potential for the solution that we're proposing in the paper to deal with the increased concerns around dynamic risk profiles that are presented by COVID, risks changing very, very rapidly advancing situation. So there is a potential application for this solution in this new risk space.
Thank you very much, James. Very good presentation. Thank you. We'll check if we have, I'll check with Eduardo if the last presenter, Leon, is here. If Leon is not here, we'll move on. Oh, hi, Leon. Hi, welcome. Thank you, Leon, for coming. So you should be able to start your presentation as soon as your slides are up. You may start it.
Okay, great, thank you. Hi, my name is Leon Price, and I'm here with Jingdao Chen. We're presenting our paper on dynamic crane workspace update for collision avoidance during line lift operations. So one of the most dangerous activities in construction environments is blind lifts, which is when the load is lifted, but the operator has no line of sight to the load or its immediate surroundings. And these are particularly common in offshore cranes when the loads must be picked off of boats. Is the slides getting stuck? Okay. So the current industry practice is to actually have a signal man who has line of sight to the load and then signals back to the operator about what's going on with the load and its immediate surroundings. There has been some related work to replace this using some automated features, but nobody has done a full system framework that accounts for what we're attempting to do here. So to assist in the blind lift, we developed a system that takes input from the crane encoders, a boom tip camera, and the operator themselves. And these inputs provide us the ability to monitor the load position, detect workers, and update the environment online. So these are then graphically displayed. So the first step in building this out is to actually model the environment that we're going to be working in. So to do this, we captured 2 point clouds, one using a drone and photogrammetry, which is in the top here, and another using a terrestrial laser scanner. And this, again, allows us to model the environment as well as the crane itself. So as mentioned earlier, we utilize many sensors on the crane, to build the real-time 3D visualization. In the upper left, we see the boom tip camera as well as the boom angle sensor. In the center is the payout encoder, which monitors the length of cable from the boom tip to the load itself. And then we see the slew angle encoder, which is attached to the top of the king post. Here we further highlight the key geometries and references that we use to build this visualization. It's very important that we have the height and the radius of the boom tip so that we can accurately monitor the load position. And the boom angle is one that has a primary impact upon this. So in addition to clearly defining the geometries in the environment, we also enclose the static obstacles in the environment with a 3D bounding box in our visualization and add some offset. So when the load comes into close proximity, we're able to send a visual and audio alert to the worker. So I'll pass it off to Jingdao. Are you here? Okay, it doesn't look like he is, so I'm gonna take over. Sorry for the confusion. So the vision system is used to track load sway in order to more accurately model the load position. An intensity thresholding is used to perform cable detection when k-means clustering and the minimum bounding box algorithm are used. So the vision system simultaneously performs worker tracking on each camera frame. A combination of edge detection, huff transform, and mean shift clustering is used to identify the workers that are close to the load. Similarly to load tracking, the 2D positions can be projected into 3D for purposes of collision warning. A semi-automated obstacle handling system is used to account for objects that move in and out of the workspace, such as containers. The crane operator is able to click on relevant obstacles in the bottom right section of the user interface, which will then create a 3D bounding box in the crane workspace for collision warning purposes. So this visualization shows an example of a situation where a worker is standing too close to the load. This occurrence is detected by the vision system, which signals the collision warning system to issue an alert to the operator in the form of audio warning, as well as a flashing red box in the user interface. This allows the operator to take necessary preventative action to avoid collision. In the experimental setup used in the research is as follows. Oh, I'm sorry, I'm light ahead here. Looks like it may be a little bit delayed. Okay, here we go. So here we look at the experimental setup used. We use several cardboard pieces to block the operator view in the cabin, which simulates the blind lift scenario. And thus the operator has to rely on the 3D visualizations shown on the monitor in the crane cabin and the automated collision warning system. This video shows an example of the live visualization presented to the operator during a lift. As shown in the video, our 3D visualization system is able to track the live position of the load and present it to the operator from different viewpoints. The virtual scene closely matches the actual scene shown on the top right corner. So get a flavor for what's going on there. I think we're ready for the next slide. Okay, here we go. We then analyze the accuracy of the encoder system based on the height estimation and radius estimation errors. The height estimation has a higher error when the crane is loaded compared to when the crane is unloaded due to the deflection of the boom. However, we were able to reduce the error by applying a statistical offset to measurements when the crane is loaded. We also analyzed the performance of the vision system for load tracking based on the metrics of the centroid error, the corner error, and the rotation error. The results show that the k-means plus block detection plus min-box algorithm had the best performance. Next, we analyzed the performance of the vision-based worker tracking system based on the metrics of centroid error, precision, recall, and F1 score. The results show that the Huff transform plus mean shift algorithm had the best performance, which is a centroid error of 0.02 meters, 20% precision, 73% recall, and F1 score of 30. So in conclusion, we implemented a real-time crane safety monitoring system for blind lift operations, implemented a real-time vision-based load positioning and worker detection system, identified an effective user interface design for the 3D visualization system from the operator's perspective, and validated it in a real crane yard. And here are just a few of our references for y'all to refer to. Thank you.
Thank you very much, Leon. We'll check if we have the first presenter, from the previous session. If he's not around, we'll start the Q&A. Eduardo, is Mezad here, or should we start the Q&A?
Q&A, Kassan.
Okay. Thanks, Eduardo. Okay. Thank you very much to all presenters. I will check first if we have some question in the chat. We have one question to presenter A, to Martina. Can you see the question, Martina?
Yes, I can. Thanks for the well-prepared presentation. Do you plan on applying this technique on different problems in the manufacturing of buildings? Yes, actually, we are currently implementing it with other software, but a very similar workflow in Unity for formwork installations. And we are open to implementing it for anything that needs visualization on a construction site. So, yes.
Yeah, I don't see here other question from the audience. I can ask some questions. I have a question to Patricia, which is similar to the one that was asked for Martina. What you applied in terms of generating the CNC code from BIM to do 3D printing, can't you use the same methodology for other type of building products and systems?
Yeah, actually, that is also used for example, metal. Using metal as a printing material. You can also use it with sand that later uses cement paste as a binder. So most of these 3D technologies use CNC code as an interpreter to control them. And yeah, so it can be applied to many applications.
Okay, really a quick one as a follow-up to Patricia. You don't have any limitation or obstacle coming from proprietary software on 3D printer and the like?
There are some open PLC softwares that can be used to control the printers, but yeah, there's issues depending on the vendor of the concrete printer. That could be an issue. You have to adapt the CNC code to the specific requirements of the printer. But ideally, we are working right now with a quote-unquote homemade concrete printer. So we're using only open source.
Interesting. Thank you, Patricia. I don't have other question here, but I'll ask myself question to the audience. Ben, you mentioned further quantitative data collection to test some aspect of the mobile BIM technology. Do you have an idea like what kind of quantitative evidence would you are going to collect and generalize from sites?
Yeah, so one of the things that a lot of these platforms have in common is I reference tasks and forms. So essentially everything you do on these platforms has a fingerprint. So you can effectively see when someone has sent a task from one company to another, the time it was sent, when it was responded to. You can even pick out keyword themes, so you can start establishing trends of If there's a lot of tasks that have the keyword of fire in them, for example, you could start seeing a trend of we're getting a lot of fire tasks in a specific month. Then you could also link that to turnstile data as an example. So every in and out on a site is recorded via a turnstile. So then you could start recording the number of operatives on site versus the number of issues, and if there's any trends there. So there's some of the data flows that have already begun extracting and started to analyse. I think the key thing with a lot of these digital platforms is everything has a fingerprint, and it has data that's there to be harnessed and it's not being used. So it's coming up with some creative ways to both extract that and analyse it and establish some trends.
Yeah, thanks, Ben. There's a question that came through the chat for Martina again. Can you see it, Martina?
Yes. Thanks for your great presentation, Martina. Is there any reason you used Lua instead of any other programming language such as Python? The reason we used Lua scripts was because in the game engine, Lua AppKit was integrated. So it was the default language. It's it's not a very complicated language, and it was there. It was handy. For the Unity project, which we are doing now, the scripting is in C#. So it really depends on which workflow you're using.
Thanks. I have a question for Leon. It's interesting, really, and a very important use case you are focusing on. I am aware how accident cost in offshore and generally in oil and gas. How are you managing? Where do you store that data and how you process it in real time?
Yeah, so we actually have a computer that we store in the crane cabin with the operator. So it's an additional piece of hardware that would need to be added. At this stage, we're not actually recording all the events that are taking place, but I'm sure that would be a great addition to maybe store all the sensor data and camera, everything that's going on in visualization in the cloud somewhere for the processing if needed later on.
Thanks. James, you mentioned personalized or individualized training. Do you have an idea what kind of data you would need to implement that and where that data would come from?
Yeah, thank you, Mohammed. Great question. We the information that we need is largely stored in the facilities and asset management software on the estate that we're working with. So the data flow comes out of those systems which manage the jobs and manage the flow of contractors onto the estate. The unique piece of data that we work with is essentially the user or the contractor individual employee email address. And once we've got that as the unique field, we can leverage off that to serve up the relevant individualized training experiences.
Okay, thank you very much, James. I don't see any other questions that's coming through the chat. So I would like to thank all presenters, the audience, Eduardo to help the presenters with their presentations of the last session in this conference. Thank you very much and enjoy your day. Thank you.